now after having the idea of the boundary layer and what was the need to develop the concept of the boundary layer, what is the laminar boundary layer, turbulent boundary layer, and what is the utility of tripwire. Now we want to solve these equations with the help of the concept of the boundary layer and want to find out that what is the shear resistance offered by flat plate when it is kept in a fluid flow. So there are two methods. One method is that solve those two equations which we have just discussed, or another method is to do the integral approach. In case of the integral approach, we don't get the equation which will give you the values at different location, but in case of the integral equation we get the average value. And if our aim is to find out what is the drag offered by flat plate in some given situation, or what is the lift offered in the given situation, then we are talking about the average lift, average drag. So we are not concerned with that what is the drag at particular location and what is the lift at particular location. We are interested in the getting the final result of for that plate, whether it is a lift, drag, or other thing. So even if we solve with the help of the integral approach, we will get the correct answer. So this approach was developed by von Karman. So in his name this method is known as von Karman's momentum integral equation. This equation is developed with the help of the control volume approach without using those continuity equation and the momentum equations, which is known as NS equation. Now we are going to discuss the von Karman's momentum integral equation. Since this is not in detail as given in the syllabus, so we shall just discuss it very briefly, right. So basically in von Karman's momentum integral equation, we have a control volume, and for this control volume, this is the velocity profile inside the boundary layer. From this point to this point, this is the velocity profile, and from this point to this point, this is the velocity profile shown here for control volume, which is shown here with the help of this dashed line between these four corners. This is a solid plate. This is a solid plate where shear stress will be offered, and its value is written as tau w, and its direction will be naturally opposite to flow. Flow is taking place in this direction of magnitude u. So what is the pressure force is exerted on the left face? What is the pressure force exerted on the right place? We can find out with the help of Taylor's expansion series, and we can find out the continuity equation for this control volume, and we can write the momentum equation for this control volume with the help of Reynolds transport theorem. So we have a velocity profile inside the boundary layer for a section of size dx. This is the left portion and this is the right portion, right. And we know that delta boundary layer thickness is function of x. So here we have delta x, which is smaller than the delta x at this right section, right.